Well, pretty quick turnaround for this next homework assignment. It's due on Thursday, but it's only 4 problems and it's relatively easy lifting, honestly. We're going to go, I've got some hints on the first problem that I'll tell you at the end of class, and so remind me if we don't get to that last slide that I've created for today, remind me because I think it'll be worth your time to be able to see that one. Today we're going to be starting into chapter 13 where we're talking about the momentum depth relationships, and that's most useful in predicting what is the downstream depth in a hydraulic jump. You've used ideas in momentum before. You remember that in fluid mechanics we had 3 different types of momentum problems that we solved, and maybe the most complicated of those 3 was where we had a pipe that was changing diameter, and because of that change in diameter and the convective acceleration, what that meant is that there was a difference in velocity of the flow in and the flow out of some control volume. And also, since it was an enclosed pipe on one end, we had to account for the pressure effects that were acting on the outside of that control volume. So this is the momentum equation that you have already used in the past, but momentum principles can also apply in open channel flow. And when we apply them is when there's a hydraulic jump, because although we can use energy principles to predict a difference in depth when there are relatively gradual transitions, like flow over a step or flow when the channel gets narrower or wider. So we can use energy for that. We can't use energy principles to predict the downstream depth in a hydraulic jump because, as you'll see, there's so much energy loss in the hydraulic jump. So we have to have some other way of approaching things. So this is the momentum function. And what it's saying is that when you compare an upstream and a downstream location where the depth is changing, even when the energy isn't conserved, the momentum is conserved. And so the momentum function is saying that there is both a dynamic component and a hydrostatic component to what's being conserved. And so at location 1, if you take the flow rate through this channel and the gravitational acceleration constant, the cross-sectional area, so this first term, if you multiplied it by gamma, would give you a force, as would the depth to the centroid. So we're talking about the distance from the top of the water down to the centroid, multiplied by the cross-sectional area. So if you take this second term of the momentum function and multiply it by the unit weight, then that gives you the hydrostatic force component at 1. By the way, calculating the depth to the centroid, if it's a rectangular channel, of course, it's only half the distance down. But we'll go through an example where we're going to calculate the depth to the centroid for a trapezoidal channel because it's a little bit different. All right, so momentum is just a law of conservation that we're going to use to predict what would be the depth downstream when there is a pretty radical transition in the flow regime. And that radical transition is called rapidly varying flow. And what I'm going to show you is a couple of instances that will cause a rapid variation in flow. And what's varying? The flow depth and also the flow regime. Because upstream of this transition, conditions are supercritical, and so the depth is going to be less than the critical depth before this transition. So here you can see what this diagram is saying is that the slope before the change was greater than the critical slope. And so because it was really steep, that caused supercritical flow. You know, this depth y naught 1 was less than the critical depth. But then the slope got less steep, and in fact, after this transition, the slope is less than critical, and so we call that a mild slope. Any slope that's going to cause subcritical flow is a mild slope, and so the mild slope causes that the depth is greater than the critical depth. This dashed line represents the critical depth, and so since it's greater than the critical depth, that means that it's going to be subcritical flow. And so anytime you have a transition between supercritical and subcritical flow, when it's going from super to sub, it can't do it gradually. It has to be a really dynamic, rapid change in the depth. And that's what a hydraulic jump is. And so here they're trying to depict like the rollers and the foam and kind of the vigorous turbulent mixing that you'd see in an actual hydraulic jump. So a change in slope is something that can cause rapidly varying flow. Flow coming out of a gate. So here you can see that a plate is being lowered down into the stream, and that plate is lower than the critical depth. So this dashed line represents the critical depth. And so the water has to go underneath the gate to flow out. Now, even though the slope is mild, so here you can see that the slope is less than the critical slope. And so ordinarily, you wouldn't be able to see supercritical conditions on a mild slope. Only you'd have subcritical conditions in a mild slope. So we've got a mild slope, but this plate is obstructing the flow, and upstream of the plate, the water pooled because it needed more energy to be able to flow under this gate really quickly. Remember, equilibrium says flow in equals flow out. And when you choke the flow temporarily by lowering this gate, temporarily there's going to be more flow coming in to this control volume that's depicted than is flowing out. And so if you just think about as you were gradually lowering this gate into place, then that caused the water level upstream to rise, and it's gathering enough energy so that you can have a really fast velocity going through this small opening. And it will come into equilibrium. Maybe what we're seeing here is after it's achieved equilibrium. And so what's unnatural is that you have supercritical flow on a subcritical slope. And so something's got to give. You can't keep up supercritical flow when the slope itself is mild. And so it goes through that transition. It goes through a hydraulic jump. And it jumps up to the downstream depth that would be expected, the sequent depth. Another possibility of what could cause rapidly varying flow. So first thing to look at here is the slope. And what we have is a steep slope. The slope is steeper than the critical slope, and so it can support supercritical flow. So downstream of this gate, the flow is going along at supercritical, and it's not downstream of the gate that you see the jump, but it's upstream of the gate that you see the jump. And the reason why is that when this gate was lowered into place, it caused pooling on the upstream side of the gate, and the water pooled above the critical depth. And so further upstream, where we had supercritical flow conditions still, the supercritical flow is coming along, and suddenly there's a downstream depth that's greater than the critical depth. And so you have super going to subcritical, and anytime you have that transition, it has to go through a hydraulic jump to match the two. One last example that I've described before in class is flow down the spillway of a dam. And so that's what this is depicting is, again, we have a mild slope, but flow over some obstruction, like a dam, and then the flow down the spillway, it's gaining a lot of velocity as the water is losing potential energy, gaining kinetic energy. And so after coming off the spillway here in this zone, the flow is going supercritical, but it can't keep up supercritical flow on a mild slope, so it goes through the hydraulic jump. So those are just three illustrations of different physical features that can cause this rapid variation in flow depth. So RVF stands for rapidly varying flow. What do you think GVF stands for? Gradually, right. So rapidly varying flow is the hydraulic jump itself. So it's this dark gray shaded area where the depth is quickly transitioning from supercritical to subcritical. That's rapid. Gradually varying flow is just what it sounds like. It's where the depth is changing much more slowly. Instead of, like a hydraulic jump may have a length of a couple of meters, gradually varying flow may have a length of several thousand meters, potentially. And so where we're seeing gradually varying flow, in the first picture, for instance, after the hydraulic jump, it gradually is getting a little bit deeper until it finally matches up with the normal depth. or here in case B, the water depth is changing as the flow approaches that gate. And so here is some gradually varying flow. After the gate in case C, where the depth was low, but then it's gradually getting back to the normal flow depth. We will, after we talk about rapidly varying flow in Chapter 13, later on we're going to look at some methods that allow you to calculate how is the flow depth changing when it goes through this gradual transition. Here's the momentum depth diagram that comes if we graph this equation. And I'm going to demonstrate that, how you do it in Excel today, because this can be useful to tell you what is going to be the depth after the flow goes through the jump. Remember, energy isn't conserved, but momentum is. Now this maybe looks like a specific energy diagram, but it's not a specific energy diagram. It's just kind of coincidental that it has that same curved shape. There are differences that we'll take a look at. On the horizontal axis is the momentum function. On the vertical axis is the depth. So the way to use this diagram once you create it is that you'll have some known depth before the hydraulic jump. And so you have a known depth y1, and if you go over to the momentum depth diagram and then up to the same depth that has the same amount of momentum, then you can go over and find y2, which is the depth after the hydraulic jump. So you'll have the same momentum, the same flow rate, but two different depths with the same amount of momentum. All right, so just to illustrate the difference between a specific energy diagram and a momentum depth diagram, I'm going to create one on Excel. And if you've got your computer, you're free to follow along, but you don't necessarily have to, because you're going to get this same experience for the homework assignment. It asks you to create a momentum depth diagram, so I'm going to show you how to do that. What we're going to do is just take this given information. Let's see here. We're going to know the width of the channel, the amount of flow rate that's going through there, and that we've got various depths. All right, so there's the flow rate in terms of cubic meters per second, the width of the channel in meters. We're going to have a whole lot of various depths. H bar is the depth to the centroid, so the distance from the top of the water to the center of area. The cross-sectional area in terms of meters squared, the velocity of the water as it flows, specific energy, just to illustrate the difference between specific energy diagram and momentum depth diagram, and then the amount of momentum. And the units on the momentum function are meters cubed. Oh, that somehow got formatted along with the rest of it. Let me... All right. Well, we'll fix that in a bit. All right, so in the problem, it says that the flow rate is 15 cubic meters per second. And I'm going to just make a bunch of these because I'm going to look at all the various combinations of depth that could give me that same 15 cubic meters per second. So for 15 cubic meters per second, the channel width is always going to be 6.5 meters. That doesn't change. But what does change is we can have lots of different depths and corresponding velocities. So let's just look over the range of from point 2 to point 3, and I'm going to gradually increase the flow depth, maybe as high as, let's go 1.5, 1.75, 2, just to go across a wide spectrum. All right, if it's a rectangular channel, then the depth to the centroid for a rectangular channel, h bar, is just going to be half of the depth. So if depth is known, then the depth to the centroid, h bar, is just this distance halfway down. So it's easy for this rectangular channel. I'm just going to say it's the depth divided by 2 for the h bar. Okay. And now the cross-sectional area is going to be the channel width times the depth of the flow. And then that goes all the way through all of our variety of depths. The velocity, v, is Q divided by the area. So when we have a shallow depth, of course, the water is going to have to be flowing pretty quickly to get a certain flow rate through the channel. But then when the depth increases, the velocity will decrease. Okay, the specific energy, let me write the equation for the specific energy. E is, it's the depth plus the velocity head, v squared divided by 2g. Okay, so specific energy is the depth plus v squared divided by 2 divided by g, 9.81. Okay, so that is our specific energy. And then the momentum function in terms of cubic meters, the function we're using there is this one. So let me paste it over so we can see it as we type it in. All right, so it is q squared divided by g, 9.81, divided by a. So that's the first term of the momentum function. And then we're adding the cross-sectional area times the depth of the centroid. All right. So this is how much momentum there is for these certain flow conditions. And then if I just double-click, it'll apply that down through. Now let's do a quick diagram. We've already seen a specific energy diagram before. So a specific energy diagram is where we want to have, let me add in some data here. Specific energy would be on the x-axis is E, and then on the y-axis is depth. So this is the familiar shape of a specific energy diagram. And so, oh, did I cancel? That was the wrong thing. All right, select data. I'll have to do it again. X-axis is energy, and the y-axis is the depth. Okay. Okay. So this is a specific energy diagram. And just to maybe illustrate this, what I probably ought to do is put in a little bit more, let's see, which one is, what point is that showing? That is where we've got the deeper depth. So let me go all the way up to 3. Yeah, all right. Now in the case of the momentum depth diagram, I'll just push this aside for a moment so I can create the momentum depth diagram. So I'm going to insert a new chart. And Excel does a great job guessing what I want to graph. Wrong as usual. Let's just delete all of that. All right, so what I want to have is on the x-axis the momentum function, and then on the y-axis depth. Okay. All right, so this one is my momentum depth diagram. So momentum depth diagram is what you use for hydraulic jumps. And of course, it'll continue much further just depending on what data I include here. It's maybe going a little too far, so let's make this one depth of 2. Okay, that looks pretty good. Maybe just 2.2. All right, so the momentum depth diagram is used to predict what would be the new downstream depth after a hydraulic jump. And the way that you'd use it is, let's say that you know, back to one of these sketches, let's say that you know that before the hydraulic jump, you know, here for case B, what if it said that the depth before the jump was 0.3 meters? And we had the flow conditions of 15 cubic meters per second. The width of the channel was 6.5. So if 0.3 was the before depth, then you'd say, all right, I know that my momentum before the jump was about 12 cubic meters. So then what you'd be doing is you'd be looking for what was the next time in the momentum depth diagram that you have that same amount of momentum. Here it is, approximately 12. And so that would tell you that the downstream depth after the hydraulic jump, if you started with 0.3, it would finish with about 1.75. So that's the definition of a sequent depth. It's the depth that has the same amount of momentum. So any questions about how to throw together a momentum depth diagram? I guess just to be a good example, let me format this so it's a little bit more tidy, because I wouldn't want to show all those extra digits there. That would be, there we go, 0. Okay, and then we would probably want to put on some axis titles there as well. It's kind of in the way here.
I know you just randomly selected a range of depths.
Mm-hmm.
Is that like a typical range?
No, it's not typical. It's kind of an iterative process. You know, maybe what if I'd started at 0.01 and done 0.02? You know, like if I'd started with these tiny little depths, then it would have taken me a while before I actually saw anything. So it's just something you have to play around with. There isn't any rule of thumb of you can always start with a given depth. It's just like a lot of things, trial and error, until what you want to do, I guess, is you can calculate the critical depth. You know, and this, the point, the furthest most to the left point, that's the critical depth. So calculate the critical depth and go a little bit below that and a little bit above that, and then at the very least you'll be able to see the point in the momentum depth diagram. And the other thing is, if you know what was your starting depth, then that would be maybe as low as it needs to go. And you could go a little bit further just to make a pretty diagram, but that's a good question. All right, so last thing, got to put on some axis titles. So on the horizontal axis was momentum, and the units there are cubic meters, and then on the vertical axis is depth in terms of meters. All right, so now we have a proper momentum depth diagram. You don't have to solve for the jump depth using Excel. There are direct equations that will allow you to calculate what's the downstream depth in a hydraulic jump. And the principle here is that the momentum is conserved through the hydraulic jump. And remember that we've previously defined how to calculate the Froude number, and this is even if you have a trapezoidal channel, this top formula will work. We'll have to skip over the videos today because we've got some extra ground to cover. They weren't that good anyway. If they were good ones, we would have watched them. The Froude number, if you have a rectangular channel, is a little bit easier to calculate because you can determine the flow per unit width, lowercase q. But just remember, if you've got the Froude number, then you can graphically identify the conjugate depth, and that's just another name for the sequent depth, meaning the depth after a hydraulic jump. And so I kind of guided you through that process where what you do is you start with, you know, a whole range of flow depths, and you find out what is the momentum equivalent for those range of flow depths. And then if you have a starting depth, you go and find the same amount of momentum, but the depth that is the subcritical version of that same amount of momentum. So below, on the underside of the momentum depth diagram, is supercritical depths, and then above the critical depth is subcritical depths. And so Y2 is subcritical, and you can see in this case, if we started off with a original depth of 0.6, then that means we're looking for a momentum of about 5.33. And so that would be between 1.2 and 1.5. And so here, as they're doing it graphically, you can see it looks like it's around 1.4 is the depth for the downstream. this Bellinger momentum equation is a way to solve it without using the graphical approach. And it relies on the upstream Froude number. So if you calculate the Froude number at 1, then you can find Y2, which here what we're saying is the Y2 is the depth after the hydraulic jump. Y1 is the depth upstream of the jump. Y2 is the depth downstream. And if you go through different textbooks or different reference manuals like the one for the FE, you'll find a variety of different ways of expressing this Bellinger momentum equation. Here you can write it as a function of the Froude number. Sometimes it's a ratio of the critical depth to the upstream depth. You'll notice here, though, that it's this term to the third power, whereas when we're doing it with the Froude number, it's just the Froude number squared. Both of those will give you the same answer. Now, there's some assumptions here, though, and when we actually go into the lab, I hope that we'll have some time on Thursday to go play around with the flume and see more about the hydraulic jump. You got a sneak peek of it last time we were in the lab. You saw that jump that was going upstream as the water encountered the broad-crested weir. What we'll do is we'll set up a stable jump because of an underflow gate in the flume. But what we'll see is that we can use this Bellinger momentum equation to predict what is going to be the downstream jump, and it's kind of okay, but it's not exactly right. And the reason why is that the Bellinger momentum equation has some assumptions built in that aren't really true. You know, like in the same way that we were using the Bernoulli equation with mixed results, like it's okay, it'll tell you the downstream pressure, but Bernoulli equation had some assumptions like for an inviscid fluid that's incompressible, and both of those things are mutually exclusive. So here, what's really not right is it's assuming a uniform velocity distribution. So that means if you've got a channel, like a rectangular channel, and the water's going through that channel, this is like a front view of the channel. The uniform velocity distribution is saying now if we have our side view of the channel here, here's the bottom of the channel, here's the water. In reality, what we know about velocity distribution is that the water velocity is slow at the bottom and it speeds up towards the top because of the no-slip condition, because of the fluid viscosity. Another way to think of it is because of frictional losses. The water that's encountering the bottom of that channel, the channel is resisting the movement of the water in the opposite direction of its flow. So the reality is that we don't have a uniform distribution, but the Bellinger momentum equation says the math sure is a lot easier if we assume that the velocity looks like this, that it's the same everywhere, regardless of depth. So that's one issue. It assumes hydrostatic pressure distribution, which it's not the end of the world. What we're saying is even though the water is moving, we're going to say that the pressure increases P equals delta H times gamma. Now, you're only supposed to use that in static conditions, meaning that the water isn't moving. And what we're going to be applying that to is water that's moving. And so the pressure distribution isn't exactly hydrostatic when you have moving water, but this isn't the worst of our assumptions. Probably the uniform velocity distribution is the worst. Horizontal bed is another assumption. So the steeper the channel is, the further away we'll get through the assumption of a horizontal bed. And this last one of boundary shear stress is negligible. That's kind of the same thing as the uniform velocity distribution. So the reason why we're assuming a uniform velocity distribution is because we're assuming that there's no shear stress at the bottom of the channel. So in other words, the water is slipping over that surface without any resistance, because this Bellinger momentum equation itself isn't accounting for energy loss. There is energy loss in a hydraulic jump, and we have a separate equation that allows us to estimate how much energy loss there is. But this isn't accounting for energy loss just because of interacting with the bottom of the channel. It's kind of just, there is some energy loss having to do with turbulence, and we guesstimate that based on the Froude number. I think guesstimate, that's the first time I've used that phrase in any of my classes, so hopefully we won't have to say that too often. We'd like our equations to be more precise than guesstimate. All right, like I mentioned, we can kind of approximate the energy loss that happens when there's a hydraulic jump, and this is the approach that we used to do it. We just take into account the difference in the downstream and the upstream depths. So just to get an idea of the magnitude of how much energy is lost in a hydraulic jump, we'll do a calculation in a minute. But actually, hydraulic jumps are sometimes forced because it can be a useful way of dissipating energy. Remember I told you about the V-notch weir when we were down in the lab? How come V-notch weirs are used in environmental engineering? Do you remember what was the attraction of that V-notch weir? Oh, that's right. Yeah, the velocity exits the tank very gradually. And if you've got a tank where the whole point is settling particles, you don't want to have a big outflow velocity because it'll interfere with the particle settling. So sometimes low velocities are important. That example with the settling tank is one. Another time that low velocities are important is in channels that are naturally lined. If you have gravel and soil in a river, you don't want to have just a huge rush of water coming through and scouring all that sediment away. And so anytime water is going down the face of a dam, remember it's supercritical and it's got all of this energy as the water exits a spillway. One of the ways to dissipate that energy is by forcing a hydraulic jump in a location that you've specifically created some armoring and cladding of the channel. Oftentimes what they'll do is put big energy dissipation blocks in the channel downstream of the face of a dam just to kind of help absorb some of the momentum, and by forcing the hydraulic jump in a certain location, then they avoid the velocity and the energy being too high downstream, just to prevent erosion and scour of the channel. Okay, so here's an example of hydraulic jump. You are going to solve for the downstream depth using the Bellinger momentum equation. While you're doing that, I'm going to set this up on Excel, and we're going to see if we get the same answer for the downstream depth. So this is a rectangular channel. That makes it easy. We want to know what's the downstream depth Y2, and then how much energy is being lost. And the units here, the delta E, that's going to be units of meters. And so where it's asking for the fraction of the initial energy that's lost, that's really asking, in other words, what percent of the energy that was at 1 is lost because of the hydraulic jump. All right, you start solving with Bellinger, I'll start solving with Excel. How many of you have found the downstream depth after the hydraulic jump? Let's see, is it around about 6 meters? Okay, so in Excel, the way to handle this is we know that before the jump, it had 194.2 cubic meters of momentum. So what I want to do is find out what is the sequent depth that has that same amount of momentum. Now, just by random chance, it looks like 6 is pretty close, but we can do better than just being pretty close. What I can do is I can use a what-if analysis or just manual iteration. So I'm going to do data, what-if analysis, goal seek, and my goal is for this cell to be equal to 194.248 by changing the depth. And let's see what it comes up with. All right, it's saying 5.96 meters. I see some nodding heads agreeing with that. Let me pull up the hand calculations that I have for this one and see if we're all on the same page for the downstream depth. All right. Okay, so we have a rectangular channel, 123 cubic meters per second. I found the flow per unit width and then the Froude number from that. Or you can get the Froude number the other way, the full way. Put it in the Bellinger momentum equation. Yeah, 5.956 meters would be our downstream depth. Any questions how to apply that equation? No? What does it assume? Remind me. Why isn't it ever going to be accurate? Uniform velocity distribution. That's kind of the real weak point. There are other approaches that don't make that same assumption, but it's not the sort of thing where you can just, in a tenth of the page solve for the downstream depth. I mean, this is usually good enough for the quickest approximation. Now, the other thing it was asking in the example is what is the fraction of the initial energy that is lost through the jump? So how effective is this hydraulic jump at dissipating energy? Okay, so the energy loss, the delta E, is going to be about 6.45 meters. And the initial energy, if you looked at the flow conditions before the hydraulic jump, so the initial energy was going to be the depth and the velocity head. And it was really moving fast in that initial shallow depth. Had a velocity of 15 meters per second. And that's getting so fast that I could peel the paint off the walls. It's really moving fast. So 12 meters of energy, and so the 6.456 meters, the fraction of initial energy that's lost, so the lost relative to the initial energy being 0.51, that means that through the hydraulic jump, we're dissipating 51% of the energy that was there initially. So the other way to calculate that would just be to find what is E2. So E2 would be the depth, the corresponding velocity head. And so that's effectively what this delta E equation is doing, is it's finding out how much of the energy that was there initially is lost through the jump. Any questions? I see people copying, and that's good. I'll leave this up for a second. All right. The delta H in the two examples I've done so far has just been half the depth. That's not the case if you've got a trapezoidal channel, though. It's a little bit trickier to find the depth of the centroid if you've got a trapezoidal channel, because you have the effect of these side triangles, right? And so the depth to the centroid for the side triangle is 1/3 of the distance down from the surface. And so there's kind of like a spatially weighted average that you have to conduct. What I've got here on the screen is a formula I found for if we have a trapezoidal shape, how to find the distance up from the bottom. And so therefore, if you can find the distance up from the bottom, then the distance down from the top would just be y minus that distance up to the centroid. So using this as a illustration, what if we had a depth of 1 meter, the bottom of the channel is 3 meters in width, and then we have 1-to-1 side slopes. You're going to need to do this on the homework, so let me just show you on the whiteboard how we could calculate the h-bar. You need the h-bar for the momentum function, right? Okay, so in this case, the area is 1 meter, and then the uppercase B, by the way, if it's 1-to-1 side slopes, and it's 3 meters at the bottom, so lowercase b is 3 meters, uppercase B is going to be 5 meters. Because for every meter of depth, and we have a depth of 1 meter, y equals 1 meter, then that means that this side triangle here is going to be 1 meter. And then there's 1 on each side. We've got the 3 meter bottom width, and then this top part is 3 meters, and then 1 on each side. So we can calculate the area as y times b, uppercase B is 5 meters, plus lowercase b is 3, divided by 2. Okay, so the cross-sectional area is going to be 4 meters squared. But then the distance up to centroid, okay, so if we do the substitutions there, it's going to be y is 1 meter, and 2 times uppercase B, so that's 2 times 5, and then plus the bottom width of 3 meters divided by 3 times the sum of the two, so 5 meters plus 3 meters. Okay, so will you put it in your calculators and see if you get the same thing that I've calculated? That says that the distance, now just think of it rationally, if it's wider on the top than on the bottom, that means the centroid is going to be more than halfway up. Does that make sense, that it would be more than halfway? Jeremy?
Looking at this picture goes with the equation, right? On the right.
Yeah, that's right.
Will we not have to flip the...
No, you don't have to flip the definitions. It just B is the top width of a trapezoid, and in our case, you know, it works out. This function works out whether uppercase B is larger or smaller.
Okay.
Yeah.
Because I was just looking at the triangle. The base of the triangle is larger at the bottom. So
You're talking about this triangle?
No, I'm talking about on the picture here. Yeah. If you chop it off where there's a triangle, the bottom has more area than the top.
Yeah, this is.
It's conceptual.
We're just we're saying this formula works if you're measuring the distance from the bottom upwards. So in this illustration, since it's wider at the bottom, then that means the center of area would be less than halfway. But in our illustration, because the top width is greater than the bottom width, I mean, just before we actually crunch the numbers, what we should expect is that it's going to be more than halfway, because the center of area, if it was just the rectangle, would be halfway, but the added width on either side is going to be bringing the average up. So 0.5417 meters is what the formula says. And so then the definition of h bar is saying how far from the water surface down to that centroid. So the center of area, if it's 1 meter, here is like the halfway mark. We're saying the center is above the halfway mark. So how far from the water surface down to that centroid? So 1 minus 0.5417. So it would be at a depth 0.4583 meters. So you can use that same approach in the homework to calculate the depth of the centroid. Let me just get that on the recording for our colleagues who aren't here today. Okay. Now, what we're going to see when we go to the lab is that the hydraulic jump, the location of it, depends on how steep we make the flume. One end of that flume has a crank on it. And so you can raise and lower the upstream end of the flume so that it can be flat, or it can be sloped, or you can actually make it adverse so that the upstream end of the flume is lower than the downstream end of the flume. So by doing that, by changing the slope of the flume, what we're able to do is adjust the normal depth that would occur. If there was no obstructions, and there's no underflow gate, and if we weren't forcing a hydraulic jump, you could just have the normal depth going through that channel. And remember, normal depth is calculated with Manning's equation, assuming steady, uniform flow. Now, the hydraulic jump can be moved around by how steep you make the flume. And the reason for that is that the hydraulic jump is matching up with some downstream depth. Now, what we consider the ideal case, by the way, this part about the location of the hydraulic jump, it's an important concept that it maybe isn't going to make immediate sense. It's the thing that really would benefit from reading through the book and kind of solidifying in your mind like the logic of why it's doing the certain thing. So what I'm saying is the ideal case is, what if your downstream depth of the hydraulic jump just coincidentally is exactly the same thing as the normal depth of the channel. And so remember, what determines the normal depth of the channel? Well, it's the slope, it's the roughness, meaning the N value, the channel geometry, just all the things that go into Manning's equation. So what we're saying is, if by coincidence the normal depth is the same thing as the downstream depth of the hydraulic jump, then that means that the hydraulic jump is going to form immediately after this underflow gate. So the rating curve, that phrase is what we use to describe the relationship between depth and flow rate downstream, where it's Manning's equation that dictates the flow rate. So here is a graph that says the relationship between flow rate and depth for both the hydraulic jump and also for the channel downstream. And tailwater is just meaning the depth of the water downstream of the thing we're focusing on. So we're focusing on this gate, we're focusing on the hydraulic jump, and the tailwater, the channel downstream of that, its flow behavior is just governed by Manning's equation. And so we can kind of control this hydraulic jump by opening and closing the gate. And if we close this gate a little bit more, then that's going to change the Y1. That would make it even smaller. But if we open the gate a little bit, then that would make Y1 bigger. So the downstream depth, Y prime 1, by the way, this warning here, new variable definitions, the Y prime 1 is what we're saying, that's the conjugate depth, meaning after the hydraulic jump, the one that the Bellinger momentum equation predicts is going to occur after it goes through the hydraulic jump. So to understand what makes this ideal, maybe it'll help to see a non-ideal case. And so if it so happens that the tailwater depth in the channel downstream is less than the conjugate depth of the hydraulic jump. So if you do Bellinger's momentum equation, here's your y1, which is governed by how wide open the gate is. And you do the momentum equation, and it says that y prime 1, the hydraulic jump should go up to here. But the hydraulic jump can't go up to there because there isn't any water at that depth downstream to match it. Like there has to be a depth match for it to go through the hydraulic jump. But just by virtue of the slope and the flow rate and the roughness, and in other words, the tailwater conditions, y2 is saying that the normal depth is a little bit lower than what the Bellinger momentum equation is predicting for downstream of that hydraulic jump. And so what happens is that the hydraulic jump has to move downstream of normally where it would have been. Look how much closer it was in this first case. In the first case, it was just right after the gate. But now it's further away. And the reason why it's further away is that as it's further away, it's going for this gradual variation. You see how the depth is increasing a little bit? So this y prime 2 is saying after the water is going through this gradual transition and it finds the depth that actually now finally matches up with the tailwater downstream. So y prime 2 is going to cause the hydraulic jump because this is the depth, the downstream depth that's supported. So if we're going to try and depict those two rating curves, the tailwater rating curve is lower than the theoretical rating curve of the hydraulic jump. So this is a dashed line because the hydraulic jump isn't actually going to set up when the tailwater curve is so much further below it. So this case is going to cause the jump to move away from the gate. If it seems like I'm talking gibberish right now, that's kind of like how it goes with this. It's pretty complicated, like the if-then, like why it's happening and what it all means. This is really one of the cases where it's super important for you to read through the corresponding textbook section. It's not just going to be enough to see the demo in the lab and then understand it. You'll have to read the book, and then maybe the demo in the lab will help to seal the deal. Okay, so this is why the jump moves downstream. In other words, it couldn't go through the jump that would have been predicted because the water just wasn't there for it to happen. The other case is if the tailwater rating curve is above the rating curve for the jump, then what it causes it to do is instead of running away from the gate, it causes the jump to approach the gate and then actually flood the hydraulic jump. So the water downstream, look at for a certain flow rate, for a certain Q, what this is saying is that you need to have in the channel downstream a pretty deep depth for a certain flow rate. So the depth has to be higher for a certain flow rate than the hydraulic jump needs it to be. And so for this channel downstream, it has kind of like, you can think of it this way, a poor conveyance capacity. Maybe it's a really rough channel or the slope is too mild, but for whatever reason, just the water isn't moving out of the way very well. And so the water is, there's so much water pooling and collecting downstream that it actually submerges the hydraulic jump, and you won't see the hydraulic jump. It'll still be there. It's just that it won't be visible because it will be drowned. So we'll force that same case when we're down in the lab by drowning the hydraulic jump by changing the elevation of the flume. Yes?
For your graphic, you have y2 and y prime. Should that be 1, or because it's talking about y2 being greater than y?
You're talking about here?
Yeah, so there.
Okay, the prime is just always talking about what would be the depth after the jump. So what this is saying is, let me. Oh, I think I see what you're saying. Yes, you're asking.
So should that be a 1?
Yeah, the subscript should be a 1. Yeah, thanks for noticing that. Good catch.
I think it's on the last slide as well.
Okay. Yeah, I'm gonna have to actually. I'll get back to you on that one because I need to think through it again when I'm not. my brain doesn't work as well when I'm staring at it now as it will in just a few minutes. So let me get back to you, and in the next class I'll make a note that we need to discuss that. All right, there's one more tip that I need to give you for problem 13.1, and what sometimes throws people off on this problem is they ask you about how heavy some concrete blocks would have to be. These concrete blocks are inside of a channel where there's a hydraulic jump occurring, and they give you a coefficient of friction. You know, how easily the blocks would slide along the bottom of the channel. And so in that problem, they tell you the depth before the hydraulic jump, and they tell you the depth after the hydraulic jump. And so what you need to do is calculate the force acting on the front side and the back side of the block. So find F1 and F2, and then the difference in force between the two. And then the weight that's required would be that force differential divided by the coefficient of friction. So in other words, the coefficient of friction is just the ratio of the force differential and the weight of the blocks. And so the blocks is going to have to be weighing more than the difference in forces because the surface is a little bit slippery. It's not, I think you'll see what I mean. That's the formula you should use. Okay, so we'll meet here in the classroom on Thursday. We'll go through a few things in the classroom, then we'll go down to the lab and take a look at the flume. That's it for today. If you have any questions on how your exam was graded, feel free to stop by during my office hours, and I'd be glad to go over it with you.